think I'm the last speaker, so I'm going to congratulate the organizers for putting on such a good workshop. And I'd like to not really thank all the other speakers, because you've given me such a hard job to follow, because you've all been so good. But I'll try and keep it interesting for the last talk. So I'm going to cover a couple data assimilation from my own work is ocean atmosphere data assimilation. But I'm going to cover land surface and atmosphere, basically by the work done by Patricia at ECMWF. So let's start by just getting some notation out there. 40 var. I think everyone's covered all these equations, but our notation that we use there, we all recognize these equations, so I'm not going to go too far into that. But what I will do is just highlight that if these things are coupled, we can talk about what's actually coupled in these equations. So if our background error PB is coupled, then we have a background error covariance coupling. If our nonlinear, or if our generalized observation operator G has coupled terms, it could be coupled observation operators in there. It could have coupled nonlinear trajectories as we propagate through the 40 var, or in the forward step of the 40 var. If our tangent linear and adjoint is coupled, that gives us something. We could have coupled Jacobians. Coupled observation error covariance matrix. Does that exist? I don't think so. I've not seen that one. Let's cross that one off. I don't know errors in observations of one thing in one state being correlated to errors in a different observation of something in a different state. So if anyone knows the example, let me know, and I'll not.
There's certainly, for instance, coupling of sea surface height variability with wind.
But
in the errors as well, obviously. You know, when the sea is rough, the errors are going to be bigger. And so depending on the area in the wind, you're also going to have different errors in the sea state.
Okay, right. Okay, it's back in. Thanks, Michael. And then also what's important is that when we cycle our 40 var, we use this bottom equation, and if keep it. If that is coupled, then we have a couple model which is going to cycle our analyses. Sorry, drop back in. So then just some technical challenges. We've got a coupled state which has two components, just for simplicity. If we just think about what we have to do technically, well, these states can be on different grids. One could be a spectral representation, one could be a grid point. We deal with big parallel systems, so they can be on completely different processors. If it's in a code, it can be in a different place of the code, a different module. What's going on? It might not be the same code. You could be running a coupled system with two separate codes that might not even be in the same language. So before we try and do the mathematics of coupled data assimilation, it's a big technical problem. So it's difficult. But one of the main things we want to consider is that we probably don't have access to these operators. So if we wanted to do the full coupled system, we would have to have all these observation operators coupled as we think that they should be. But in general, we don't have access to these observation operators. So a coupled assimilation problem is, what do we do in the absence of these coupled operators? And what can we get with just some of them being present? How do the systems behave? And overcoming all the technical challenges as well. So what I'd like to think about is the timing of an observation in one component having impact in the other. So if you write down the 40 var, the gradient of the cost function, and imagine you have an observation in one component and not the other. And if any of these terms here, so this G, this H, this M, or the background error covariance matrix, if they have the appropriate off-diagonal terms, so the coupled terms, then what you get is that you get a non-zero part of your gradient in the other component. So that means that as you do your 4D var, an observation in one component gives you an increment in your other component immediately during your assimilation window. But if you don't have any of those things, oh, that's wrong one. If you don't have any of those things, but you have a, go away, you have a coupled model, then the coupled model which cycles the assimilation won't give you your immediate observation impact across components. It comes later. It comes, depends on where the observation is, depends on how long that, the mechanics of your model propagate that signal across the boundary, but it will come later, not in that analysis cycle. So that kind of leads us to a categorization of coupled DA. So if you have an immediate observation impact at the analysis time, you're kind of strongly coupled somehow. If you don't have that, if it comes later, that's weakly coupled. And we get some formal definitions here. But what I would like to say is that these terms don't actually tell you what's coupled. I listed a load of things which could be coupled. I haven't told you what ones are with these strong and weak words. So it's kind of a nice categorization, but if you read a paper and it says one of these words, you can't compare it to some other paper with these words. Like, it can be useful to talk about what's going on and comparing some experiments from one place, but we actually need to be more descriptive about how we're doing our coupled assimilation and so on.
You are including in this weakly coupled assimilation also. For you, this weakly coupled assimilation also include the case of when you use the full nonlinear model in the outer loop of a 4D var, or that in your case will hand into strongly coupled?
So
I'm not talking about the next cycle.
Yeah. So that term's here. So we get an increment within the analysis cycle. So it's in the class of strongly coupled. Okay. But it could be a lot stronger if you put more stuff in. It's not very descriptive to just say strongly. So I'm going to sort of not call it strongly anymore. I'll tell you what I'm going to do when I'm doing that. So yeah, that's a bit of my soapbox for that. So at ECMWF, what do we have? So we have a Earth system model. So it's got a lot of components. It has the atmosphere, which you would expect for doing numerical weather forecasts. But it also has land, it has lakes, it has waves, it has an ocean, and it has sea ice. We almost have rivers. They're in a sort of side project. We have the information in-house, but it's not built into our IFS. So what we want to do is we want to take information from any of these components and use it to improve our atmosphere and our weather forecasts. So let's start by talking about the land surface. So what we're going to do is we're going to have a weakly coupled land surface data assimilation scheme. So by that I mean that the only coupling will come through the non-linear cycling of the model. And why can we get away with this? Well, so basically, for numerical weather prediction, we're going to have a 12-hour assimilation window, essentially. And we have, for operations, we have a 9-kilometer global grid. So at these scales, spatial and temporal scales, the land surface doesn't really interact horizontally. You don't get long interactions horizontally. What you get are vertical processes happening in these timescales. So really what we want to consider is the vertical and time for each grid point. So we have a 2D problem. We don't have everything interacting as in the atmosphere in this 4D problem. And also, once we have this, a weakly coupled system, we can basically simplify this by turning off our atmospheric 40 var, which is really expensive compared to a 2D land surface problem. And we can test this really quickly. So we have a system where we get some of the coupling, but it's hugely cheaper than running the whole weakly coupled system, and we see the impacts. But this isn't without its problems, so any fast processes which are going on, we're not going to get immediate impact from these fast processes into initializing our forecasts. So here's a schematic of what it looks like in our system. So we have a 12-hour data assimilation window going from 9 o'clock at night to 9 o'clock in the morning. And we start it by running a nonlinear coupled trajectory. Then once we've run this first trajectory, we go and do our 40 var in the atmosphere. I'll say no more about that. Massimo talked about that earlier in the week, but it's complicated, it's expensive. While that's running, we also do land surface assimilation. So we have some components where we do 2D OI, so for a 2-meter temperature and a 2-meter relative humidity, we do an optimal interpolation. We have to figure out where the snow is, but I'll skip that. And then we run the soil moisture assimilation. So we do that via the EKF. I'll tell you some more about that in a second. The important thing is the results of these analyses go into the next assimilation cycle. They're combined for the next one. So we don't have interaction between the 40 var and the land surface during this assimilation window. And in that sense, with these previous definitions of way of thinking about this, this is weakly coupled because the observations here are
right? So this is the screen level temperature that you are assimilating to compute the soil moisture, right?
Yeah, but we start, basically it computes its observation departures in this nonlinear coupled trajectory. So it's not the result of the 40 var minimization giving us an update to the screen level temperature. It's basically the first guess. So they're separated. We could improve upon it and add more coupling to do that, but this is what it is. Okay. So why do we want to do this? So basically, a soil moisture analysis gives us impact into our numerical weather forecast. So in red, what happens if we don't do any soil moisture analysis? So below 0 is good here. In the 0 line is what happens if we do basically our original soil moisture analysis. And then the black line, which you can see improvements in northern hemisphere surface temperature and humidity in both seasons, if we basically tune our observation error covariances. So we actually have a good representation of what the observation errors are. We can get improvements to the forecast out to day 5 in surface temperatures. So it's worth doing. So let's tell you about what we do. So we do an EKF. So we have our Kalman filter equations, essentially. Our state, our soil moisture state, we have 4 levels of soil. And our state is going to be the top 3 soil moisture grid boxes. The deep soil moisture we don't analyze. Observations which we use are going to be pseudo observations of the 2-meter temperature and the relative humidity, which we just mentioned. But then we also have satellite information. So we have soil moisture coming from ASCAT, so a scatterometer. And also just this year, we've implemented soil moisture observations coming from SMOS, which we derived by a neural network. So we can tell you more about that offline if you're interested in how we use the neural network to derive soil moisture. So then we have our observation operator, which is the model equivalent of these things. So the question is, how do we calculate the Jacobians, h, to go into this equation? Because these Jacobians are essentially Jacobians of running the nonlinear model, coupled ocean, land, atmosphere to the correct time, and then taking the observation equivalents. So the first thing that we did was we just do a finite difference approximation. So we perturb all the top level of soil moisture variables, run the coupled land atmosphere model, and compute the finite differences. And we do that for all the soil moisture levels we're interested in. And what that means is that we have to run 4 coupled land atmosphere trajectories. So that's pretty expensive, but works. And all these plots were using this perturbed trajectories idea. But what we've just implemented is actually using our ensemble of data assimilations to directly estimate these covariances. So we estimate these from our ensemble of data assimilations, and now we don't have to run any of these perturbed trajectories, because these are all available offline. And in terms of computational cost, what this has done is it's reduced the computational cost in seconds by about a factor of 3.6, I think it is, because we're saving those 3 out of 4 trajectories. So the result of that is you can basically ignore the red line, just look at the black line. Forecast scale scores, which are almost identical to what we had before. So what we're doing here is we're saving computational effort, and we're actually getting the same quality result. So that's really good. But what I'm interested in, and I don't know the literature enough for this, is that, so I should say in their SEKF, we keep our background errors P fixed. So it's not an ensemble Kalman filter where we estimate this from the ensemble. All we're estimating is our Jacobians. But we have to localize our Jacobians to make this work properly. So what I don't know, I'm sure someone will be able to tell me, is the literature for not localizing P, but for localizing H. And any kind of analysis which anyone's done, I'd love to know more about. So you can tell me later, or when we have questions, if there's some theory for doing that. Okay, so that was the land. That's what we're doing for land. Now, what do we do for the ocean? So basically, last summer, we implemented a new cycle, and that meant that all our forecasts are coupled. So we put in the land and sea ice coupling into all our forecasts, so anything a user gets has been run with a coupled model. So basically, to run with this coupled model, we have to have an ocean analysis system. So in the ocean-only context, we still don't have all these operators which we would like to use. So for example, we don't have the adjoint of our ocean model. So that means that our methodology which we're going to use is 3D var FCAT to find our analyses. And the ocean is pretty slow. There's a lot fewer observations in the ocean than the atmosphere, so we have a long time window. And that time window ranges from 5 to 12 days. This website is brand new. I'm going to have a look at it. It's literally just gone online this week. And it is near real-time monitoring of the ocean. And anyone should be able to see it. If I have I got Wi-Fi? Yeah. Well, here's one I loaded earlier. Basically, you can come along here and you can pick which variable you're interested in. So sea surface temperature 2 days ago. You can look at the full field. You might be able to look at an anomaly if it's loading. Well, I would encourage anyone who's interested to have a look at what's going in the ocean to go to this website and have a look, because there's some pretty, very, very pretty pictures going on there. So basically, how do we build a coupled assimilation given all these lack of observation operators, not observation operators, just general operators? So what we can do is we can just throw all our observations, all our operators into one system and see what we come up with. So in orange, we have things which are uncoupled, so block diagonal terms. And in blue, we have terms which we have the coupled versions of. So what we can see is that we only have really coupled model evolution in here. And we can cycle our model with a coupled model, cycle our analysis with a coupled model. So plug that in. What that gives you is essentially the outer loop coupling. So every time we do an outer loop in 40 var, we're using a nonlinear model. And this has been used successfully to produce two different reanalyses. So a 20th century reanalysis and a satellite era reanalysis. And these data sets are available to anyone through the ECMWF website if you're interested in looking at coupled reanalyses. I'd encourage you to go and look at them. But we want to go to numerical weather prediction using in a coupled way. So if we were to do this, this would require aligning our assimilation windows. So if we just write this down, we have to write down one assimilation window for this 40 var system. So there's a problem with that. And that problem, Michael was talking about how well observed the oceans are these days. But this is the number of observations we might have in a 6-hour window, which is what we use to produce our forecasts. So on the left is what you see if you wait 49 hours to collect all your observations in. And then the colors are different types of observations. And the numbers on at the edge are how many of each type of observation that there are. So down here we have satellite altimetry, and we can see on the right-hand side, if we only wait 1 hour, which is a typical cutoff time for numerical weather prediction, how many fewer observations would be available. So even in the satellites, we are getting a substantially fewer number of observations arriving at ECMWF to be assimilated. So if you look at this pink number, we have 25 different observations, so profiles in this case, if we wait for 2 days, but we have none if we try and do it when we will actually need to do the assimilation. So these pink profiles are down here, there's some up there, and there's some in this region. So if we just immediately went to do this for numerical weather prediction, we would be putting these guys out of a job. These are elephant seals with sensors stuck to their heads that actually send us data. And they're very useful because they swim by the ice edge. We get information where Argo floats basically don't go and other observation types don't go. So what we don't want to do is we don't want to lose observations, because we can come up with the smartest assimilation scheme that we like, but if we don't have observations to put in there, apart from Jochen, he's the only one who can do assimilation without observations, I believe. But I can't, so we have to come up with a way to basically allow us to use observations which don't arrive for the schedule which we would like. So our system looks like this. So we have these long bars going from here from 1 up to 9 are our ocean assimilation windows. And as you can see, as we progress to the next day, this goes from an 8-day assimilation window to a 9-day, 10, 11, 12, and then we shift the whole thing and start again. So what we do is we put in our 12-hour atmospheric analysis windows at the end of these. And these arrows tell us where the information goes. So if we consider this point here. We're going to do a 12-hour atmospheric assimilation window, build up the forcing over those 12 hours, and do the next one and have more forcing. And then that will allow us to do a ocean analysis. And then once we've done our ocean analysis, the boundary conditions from the ocean analysis will go into our next atmospheric analyses. So in this way, we don't have immediate observation impact between the two systems, but because we have this staggering, we have this delay, and it's weekly, falls into this category of weekly coupled assimilation with a implicit 24-hour coupling period. But if we just blindly do this, our systems are going to have completely different biases. So we're comparing basically an uncoupled assimilation, which sees nothing to do with a numerical model, or our ocean analysis, which has a numerical model built in. So we've got to be careful. And basically in the ocean, we have far more effective resolution in the tropics because our Rossby radius of deformation changes with latitude. So our eddies are much smaller at high latitudes, and we don't represent them as well. So what we're going to do is we're going to only couple SST in the tropics where we know our analyses are good. We're not going to couple it in the extratropics, and we are going to couple our sea ice because we know our sea ice is quite good relative to the other observations which we've got. So here's an example of what things can look like. So on the left is a manually produced ice chart. So you can see high ice around there going down the coasts. Here we have what a satellite can see and can see well. So it can only, so this is the Baltic Sea around Finland. So our observations basically can't get close to the coasts because of the footprint of these microwave radiometers. If we have an uncoupled analysis, you see lovely Gaussian structures, which are in no way related to what the actual ice is. But if we use this weakly coupled system, basically we're putting in a dynamical model of the ocean and sea ice, and that is giving us very representative structures for our ice. So this is what it looks on a local scale. If we look at forecast error maps, we can see basically, in this case blue is good, we can see that we're improving skin temperature down here and basically a surface temperature of the atmosphere up here in all the regions where we're doing coupling. So coupling SSTs in the tropics and coupling sea ice. But this also extends up into the atmosphere. So it's not just the surface variables where we get these improvements. We also see basically the propagation of information from the surface up into the atmosphere. So you can see all these regions where basically that information is better than the other information we were putting in. And so we're getting this propagation vertically. But we would like to go to a bit stronger coupling. So we have to bear in mind all those issues. So we basically, if we go to outer loop coupling like the Sierra system, we're just going to lose observations for NWP. So we've got to do something different. And that something different is what we're considering now, where we're going to take our background term, which we're going to use to start each analysis with all our coupled operators. Well, we're going to cycle our atmosphere, as we would do, but our ocean initial conditions, we're always going to start from our weakly coupled system. So the system where it has these really long analyses windows. Okay. And what does that look like? Well, it's the weakly coupled system, but each time we do an atmospheric analysis, we're doing outer loop coupling. So we have immediate observation impact from the observations which have arrived across the domains. And, well, what does that look like? So if we measure against some observations, look at first guess fits, it's pretty neutral. So aircraft and against GPS radio occultation observations. So neutral is what we want, because if it's been worse than neutral for a while until I'm finding what needs to be ironed out. But we're getting some positive impacts. So the bar has now changed. So these impacts are on top of what we got from the weak coupling. So our baseline is now doing weakly coupled assimilation. And so we're improving things in vector winds in different regions. And that information is moving up slightly into the atmosphere. So basically we have to, we want to go to coupled assimilation for all these reasons. In particular, it'll allow us to use coupled observation operators, which should give us some benefit. But we have to make sure that it's going to work with observations which are available in real time. And actually, these tests haven't quite tested what would be available for the ocean in near real time. And then we also have to show it improves our forecasts. Otherwise, I'll not be allowed to implement this. So I shall finish there and say thank you.
All right, we have time for some questions.
I think I have many, but we may discuss it offline. But I'm just curious then to understand. Could you say you were you were saying that you need localization, but you would like you were posing a question to the audience at that point. You were saying that you would like to move the problem of localizing P to the problem of localizing H.
Well, that's what we have done. So we are localizing on H. So basically, what we were seeing is when we were comparing our finite difference calculations of these Jacobians to what we were calculating from our EDA, that we were getting spuriously large increments at depth. So
you cut them away.
Yeah. So we localize in the vertical on our H, not our P. And it works well, and it can deliver neutral results, but I've not really thought about the mathematics of what that means in relation to how the ensemble Kalman filter works.
It's younger.
Working? Yeah. Just to react on that, I mean, it's all localization, right? So we localize PHT and we localize P, what is it, HPHT. So that's what we are localizing. So the theory is there already.
But
I think. I mean, there's no theory. That's what.
So if we think about it, over here I'm applying the localization twice, whereas in
yeah. So I think you should do it once on the whole thing, because that's the effective matrix that you have.
Yeah. So, but the traditional way would be to localize P, so you apply it once here and once there. Whereas in our case, we're applying the localization to H here, so once, but then twice over there. So we get this possibly a mismatch of scales or something. I'm not doing it.
That's what I'm trying to say, right? I think we are localizing PHT and we're localizing HPHT. And we're not localizing P separately or H separately. If we have non-local observations, then well, anyway.
Okay.
I mean, it's in the end just a trick to ensure that we don't mess up long-scale correlations. So.
I think we can probably close here. Let's thank Phil again.